In the last lecture, we have seen uh, what is random process and what are the different parameters, statistical parameters which are associated with the random process. So today we will see some problems which are related to the random variables and some one problem which is related to the random process. Okay, so let us see one problem. Let us define a random variable. Uh, define a random variable. Define a random variable having a relation y is equal to 3x plus 2. Okay, and we have to find first part of the question, to obtain the mean of y. Okay, what is the mean of the y and what is the variance of y? Okay, with in terms of variance of y, in terms of the parameters of x, okay. So we will see, we will first see the answer for this, after that we will proceed. So what is the mean of y? Mean of y is nothing but, the mean of y is nothing but is the expected value of y, right? It is nothing but expected value of 3x plus 2. It is equal to, it is nothing but, by the property of expectation you can see, it is nothing but 3 into okay, we will write one more step, expected value of 3x plus expected value of 2. Okay, and this is nothing but 3 into expected value of x plus the expected value of 2, because 2 is a constant, so it is nothing but 2. So it is equal to 3 into mu x plus 2, where mu x is the expected value of x, is nothing but the mu x. Okay, so we got it. Now what is the variance of this? The variance of y is equal to variance of 3x plus 2, which is equal to the variance of 3x plus variance of 2. But variance of 2, I told you this is a constant is not varying, so its variance is equal to 0. So it is nothing but 3 square into variance of x. Okay, and what is the variance of x? It is nothing but sigma x square, so 3 square is 9. So the variance of y is equal to 9 into variance of x. Okay, so this is the first part of the question. Okay, next is the second part of the question, is what is the mean and the variance if evaluate mean and the variance of y if x is having a Laplacian distribution. Okay, so if x is Laplacian, the answer, if x is Laplacian random variable, then expected value of Laplacian random variable, you have seen from the table, it is 0, and the variance of x is equal to 2 by alpha square. Okay, so what will be the expected value of y? We have seen the expected value of y is equal to, this is the formula from the part A, so it is nothing but 3 into mu x plus 2. Since mu x is equal to 0, so 3 into 0 plus 2, which is equal to 2, right? Now the variance of y is equal to 9 into the variance of x, right? The variance of x. Okay, so this is equal to 9 into 2 divided by alpha square, which is equal to 18 by alpha square. That's it. Okay, now if what will be the variance of x and y? This third part of the question is given as evaluate the mean and the variance of y, sigma y square, if x is a Gaussian distribution, Gaussian random variable, you can say in general, random variable. Okay, a general Gaussian random variable. So for a general Gaussian random variable, you know that the expected value of x is equal to some mu x mu x, and the variance of x is equal to sigma x square. Okay, let's say this is equal to some mean m and this variance is equal to some sigma. Okay, then the expected value of y is equal to 3 into m plus 2, that's it, and the variance of y will be equal to 9 into the variance of x. Okay, that's it. So this is the case of the Gaussian random variable, some arbitrary Gaussian random variable. This m can be any value according to the nature of this distribution. Okay, from the PDF it is directly obtained. Now the last part of the question: evaluate the mean, obtain the mean mu y and the variance of y if x is equal to b into cosine of 2 pi into u, where u is a uniformly distributed, or you can say uniform random variable, uniform random variable in the unit interval. So what is the meaning of this? It has been given that x is again a function of u cosine of 2 pi into u. Okay, and this u actually belongs to, u is basically, it is a uniform distribution in the interval, unit interval. It has been given in the unit interval. So if it is given that it is in the unit interval, that means 0 and 1. So this height will be also 1. Okay, so the PDF is 1. Now we need to find first, because we know that the mean of y is equal to 3 into mean of x plus 2. We have already seen this, and the variance of y, which is equal to sigma y square, which is equal to 9 into variance of x, sigma x square. So but we don't know what is the mean of x and what is mean variance of x. So we have to first find it. Okay, we have to first find it. So how to find the expected value of x? Expected value of x is nothing but the x into, so we will first evaluate what is the expected value of x. Okay, this is nothing but, you know that the distribution is changing from 0 to 1. So 0 to 1, and cosine of 2 pi, okay, into u, and there is a b here, into du, and there is and the distribution is already 1. Okay, so you have to multiply just with 1. Okay, 1 into du, that's the expectation. So because x, you know that expected value of x is nothing but x into f of x dx anyway, but here exactly it has been given, the u has been given actually. So this is the expected value of x. So this is nothing but, if you integrate this, you will get minus b. Integral of cosine is minus sine, that's why minus b into 2 pi into du, and in the interval you have to put the interval from 0 to 1. So if you integrate this, you will get it as 0. Okay, you will be getting it as 0. Okay, now you have something, variance of x. Okay, you have to find the variance of x. Variance of x is nothing but expected value of x square, but x here it is something like b into cosine 2 pi u. So you have to take the square into 1. 1 is the PDF. Okay, don't forget 1 is the PDF is coming from here. So here also 1 is the PDF. So into du between 0 and 1. Okay, now if you integrate this, you will get it as b square into integral 0 to 1, okay, half u, because you can see you are integrating with respect to u. So you can see here this integral become half u into du, okay, plus b square by 2 integral 0 to 1 cosine of 4 pi u into du, okay, 4 pi u into du, okay. So because you have to use the formula for cosine square. Cosine square, there is a formula for that, okay, in terms of you know what is the relation between cosine x and cosine square x. So you have to use that formula. Now it will be equal to b square into 1 by 2 plus b square by 4 pi into minus of sine 4 pi u, okay, that's it, okay. Now 0 to 1, so this you will get it as b square by 2. Now you can find the expected value of y, which is equal to mu y, which is equal to 3 into mu x plus 2, which is equal to 3 into 0 plus 2, because we have got it as 0, this integral we have got it as 0, so this is equal to 2. And what is the variance of y? Variance of y is sigma y square, which is equal to 9 into variance of x, that means sigma x square, which is equal to 9 into, and you know this is the variance of x, so 9 into variance of x is b square by 2, okay. So that's it, okay. I hope this is clear to you. So next we will see another problem. You have to show that. Before that, I will introduce you three important functions. That is, one is the error function, okay, error function. So usually it is represented as ERF, okay, error function of x, you can say. So the error function of x is defined as 2 by root pi, okay, integral 0 to x into e power minus t square dt, okay. And you can see our general Gaussian distribution is having a structure 1 by root 2 pi e power minus t minus mu by 2 sigma x square into dx, almost similar to this format. So these functions are very helpful in communication theory and to analyze the probability of error of the transmission, okay. And another thing is nothing but the complementary error function. So you will see this kind of things in the communication theory. So complementary error function, okay, complementary error function. What do you mean by this? It is usually represented it as ERFC of x. So complement means what? You know that for a probability distribution, usually the total area will be equal to 1, right? So complement of ERFC means it is nothing but 1 minus, so ERFC of x, that means the complementary error function is nothing but 1 minus ERF of x. That's it, it's the complement. So it is usually the integral, it is nothing but 1 minus 2 by root pi integral 0 to x into e power minus t square dt, and this you can calculate and find the final answer as 2 by root pi into integral x to infinity e power minus t square into dt, okay. That's it. So this is the ERFC of x, okay. Please don't forget these formulas. These are all very important in analyzing the communication systems, and this is ERF, okay. And there is one more function which is known as the Q function, okay. This is known as the Q function. It's very, very important function. In again, it is another important function, and a table is available actually, Q of x table, usually represented as Q of x, okay. A table for Q of x and x is available, okay. You can find what is the value here, let's say x1, then it's Q of x1, like this. A table is available in many textbooks, and also chart is available. So Q of x1, q of x2, you can find it, and this can be used for analyzing the probability of error, the probability of error analysis. Similarly, the error analysis, simply error analysis, etc. Okay, so these are all very important function. So what do you mean by this function? How we can define it? Q of x is nothing but 1 by root 2 pi, okay, into integral x to infinity e power minus t square by 2, a small difference, okay, into dt. Okay, that's it. So this is nothing but the q of x, integral 1 by 2 pi into integral x to infinity e power minus t square by 2 dt. Okay, so this is nothing but, you can see here, you can see this is a like a Gaussian distribution. You know that a Gaussian distribution is having a formula with if mean is equal to 0 and sigma x square is equal to 1. In this case, the Gaussian distribution is having a form which is 1 by root 2 pi 2 pi, okay, 1 by root 2 pi into e power minus x square, sorry, minus x square by 2, right? So this is nothing but the Gaussian distribution. So if you compare this function with this one, you can see that it is nothing but a Gaussian distribution, and there is an integral. Integral is showing actually the area, and from what area actually. So if you have a normalized Gaussian distribution, that means a normal distribution, we will call normal distribution, okay, a normal PDF. You can see the variance is sigma x square is equal to 1, and the mean at the center, that means mu x is equal to 0. And if you consider a point, for example, if you consider a point x here, then you are integrating from x to infinity. You can see that means you are finding the area under the curve from x to infinity. This is, so this area we will call area is nothing but, it is nothing but q of x. Okay, let's say this is x1, then it is nothing but q of x1. Okay, now we will see. I hope this part is clear to you. So if you know what is the area for a standard normal distribution, that means with the unit variance and mean is equal to 0, then you can extend it for finding any other distribution, okay, any other distribution. Any other normal, any other Gaussian distribution with another mean and variance which is not equal to 1. Okay, so it can be used easily. And for this q of x, you have a chart, and from the chart you can easily evaluate this integral. Okay, so this integral can be evaluated from the chart, because it's very complex integration. Okay, it's not so easy to integrate, that's why. Now we will see what are the different things. Suppose you have a Gaussian distribution, a normal distribution with mu x is equal to 0 and sigma x square equal to 1, that's mu x equal to 0, and this is the spread, and the spread sigma x square equal to 1. Now you can integrate it from, for example, if you have a point here x, then you have the integration from x to infinity, and this area from x to infinity is nothing but the q of x. Okay, that's it. Now if you can have, let's say this is x2 and you have q of x2. Suppose you have another distribution, same thing, a Gaussian distribution with sigma x square is equal to 1 and mu x is equal to 0. Now you have a point here, let's say x3, then this area from x3 till infinity to infinity, that's it. This area from x3 to infinity, that's it. That area is nothing but the q of x. This area is nothing but the q of x. Okay, so it is nothing but the area, it is representing the area. So now we will see a problem based on this. Prove that the q of minus x is nothing but 1 minus q of x. Okay, so logically we can easily prove it actually. So you have to prove this mathematically anyway. So you know that what is q of x, we have seen just now what is q of x. So if you have something like here, right, like this q of x, if you have x here and let's say this is x, then q of x is nothing but this area, right? This area is equal to q of x. And you know that the total area under the curve is the total area is, because it is a Gaussian normal distribution, for any distribution the total area is equal to 1, right? Now you want to find what is q of minus x. What is q of minus x? Q of minus x means if this is the x, the correspondingly you have minus x here, right? Then q of minus x means you are starting from minus x and going to infinity. That means you are calculating from minus x to infinity, that much area, and this is infinity here. So what is q of minus x? Q of minus x means you have the total area which is equal to 1 minus this area, but this area, that is area number, let's say 1, and this area is just nothing but area number 2, both are same, right? So instead of this area I can use, actually I can use another area which is q of x, right? So q of minus x will be equal to 1 minus q of x. This is the simple logical proof, but we will see it mathematically anyway. So q of minus x is nothing but 1 by root 2 pi into integral minus x to infinity into e power minus t square by 2 okay, minus t square by 2 dt. Okay, so this is equal to q of minus x means you have to, this is equal to, so this is the area. That means you can see this is changing from minus x here to infinity. So this is nothing but you can write it as 1 minus the 1 by root of 2 pi into square root of, okay, 1 minus this area, right? Because you want the total area is 1 anyway, so you want only this area. So this area is nothing but you have the total area which is total, nothing but total is equal to 1, total equal to 1. So 1 minus this area, and what is this area? This area I am going to write it in blue color anyway. This area is nothing but 1 by root 2 pi, okay, integral, I am starting from minus infinity, so minus infinity to minus x anyway into e power minus t square by 2 is the curve into dt. Okay, now we will introduce a new variable t dash. Put t dash is equal to minus t, okay, just for the integration purpose. Now you will see how it will be changing. So this area q of minus x will be nothing but 1 minus 1 by root 2 pi, okay, and you know that this will be changing. If I put t dash is equal to minus t, my limit will change its polarity. This is minus, so my limit will change to infinity, and this become positive, so to x e power minus t dash square divided by 2, okay, into dt will become minus of dt dash, okay. That's it. Now we will see, so that's it. So this is equal to, I will write it in the next step, I think that's better. Anyway, I will try here itself. So this is equal to, 1 minus 1 by root 2 pi, and you know that we can change the, you can see here there is a minus sign here and there is a minus sign here. So this become 1 plus integral infinity to x e power minus t square, t dash square by 2, t dash square by 2 into dt dash, okay. So I am going to write it in the next step here. Q of minus x is equal to 1 minus 1 by root 2 pi integral I will write it again, infinity to x into e power minus t dash square divided by 2 into dt dash, but this become plus, I told you. Now because of minus dt dash, now this become 1, I am going to write here 1, but in this integral I am going to write from x to infinity. So you know that by the rule of integration, if you change the polarity, if you change the limit, if you reverse the limit, then this plus become minus. So again it will become minus 1 by square root of 2 pi into x to infinity e power minus t dash square by 2 into dt dash. But you know that this is nothing but your q of x, so minus 1. So this is nothing but q of minus x. So that's how we can prove q of minus x is nothing but q of minus 1 minus q of x. I hope this part is very clear to you, okay. So we will see one more important problem, which is related to the binary random binary wave, okay. So the question is, this is the problem anyway, the problem: obtain the autocorrelation function, obtain the autocorrelation function of a random binary wave, okay, with amplitude plus a or minus a, okay, and the time duration. So we are talking about a random process, and the time duration t, okay, time duration t. Now what I want to tell you is that we want to find the autocorrelation function, okay. So the autocorrelation function can be defined as we know that Rx of tk and ti, that means the autocorrelation between two different times, t1 t2, like this you can find any time, t1 t2 or tk ti can be written as expected value of x of tk into x of ti, okay. And also it is given that binary random wave, anyway it is a binary random wave, random binary wave, okay, you can say random binary wave, and also each binary numbers are independent, okay. Now we will see how we can obtain this. So we can first draw how the wave will be looking like, okay, how the wave will be looking like. So you have something like a minus a sometimes. This is the origin at time t equal to 0. So you have a minus a, and also it is given that also, okay, I forgot to write one more thing, okay, and the pulses given that the pulses are not synchronized, okay, the pulses are not synchronized. So it will be something like this. That means the pulse position, it is not starting at t is equal to 0. You can see it is starting after a delay, you can say. So how much time delay is there? It is nothing but the time delay td. Okay, so there is a time delay anyway. Now the pulse is like this. Maybe some for 2 intervals it is plus a, again it is plus a. After some t duration it goes to minus a, like this, and it remains there, and for 1 time duration, and again this is plus a for 1 time duration t. You can say this is t, this is t, like this. Okay, again it is going down, and maybe it may be remaining there for some 2 t duration. Okay, sorry, for t duration again here, and t duration again here in the state of minus a again. So it's a random wave anyway, so it is always changing. So each sample function will be having this kind of structure anyway. So this td has been time synchronized, and also the delay, also given that it is given that the delay td is uniformly distributed. Okay, so you have to note that this td is a random variable. It is a random variable, okay, because it will be changing. So each sample function, so different sample function will be having different td. So this is plus a, like this, okay, for t, and this is again t, like this. This is the structure. So this starting point will not be similar. Sometimes the starting point you have minus a, sometimes you have plus a, and sometimes this td will be, sometimes for example 0.1 second, sometimes it will be 0.2 seconds, so that it is the pulses are not synchronized. So in that case, how you can find what is the autocorrelation function? Okay, now let us consider how to obtain the, okay, what is the basic formula for the autocorrelation function? You know that Rx of Tk and Ti is nothing but the expected value of Tk, sorry, x of Tk into x of Ti, right? This is very clear to you. So if you are taking the random binary wave, which we have explained here now, okay, it's maybe something like this. I am just expanding the view for your understanding. Now you know that this time delay is td, as I have mentioned here. Okay, this time delay is td. Now this is the question anyway. So the time delay is td. Now I told you this is minus a, maybe this may be plus a, and this duration may be t. So these are all the different realization. All the realization will be having different form anyway, and it is not synchronized. Suppose you are considering the time t ti, let's say this is the time and this is the amplitude, this is tk. If both are in the same pulse, there is no issue. So we will but if tk is here, so tk is here, suppose tk, sorry, not here, if tk is here in the second or third pulse, okay, not in the same pulse, then is there any correlation or not? No, because you see here tk and ti are in the different pulses, okay, of the same sequence. So both are in the different pulses. That means the difference between tk and ti, that means if you take the magnitude of the difference between tk and ti, similarly you can go backward also, you can consider a tk here also, there is no issue. So the difference between tk and ti is greater than the time duration, and the time duration was given, time duration was given here. You can see the time duration is given, it is nothing but the t. So that this time duration is t, okay, the time duration of the pulse. So if this is greater than this t, then that means that both are in different pulses, both are the different amplitude, you can say, okay, or you can say that they are independent. So if they are independent, then you know that Rx of Tk into Ti, if they are independent, you have this formula, expected value of Tk into expected value of Ti will be equal to, both are independent, so you can separate the density functions. That means x of Tk into expected value of x of Ti. That means you can just simply multiply these two terms, right? Instead of taking the expectation of the product, you can product the individual expectations. So, but we will have to see what is the expected value of x of t, the random process. But we have the expected value of x of t. What is it? You know that it is having an amplitude plus a, and sometimes it is having an amplitude minus a with equal probability, for plus a and minus a. If both are having equal probability, then what is the expected value? The expected value of x of t, if you consider, it can take the value plus a or minus a. So with equal probability, that means each one is having equal probability. So half is the probability mass function for that. Each of this probability of a will be equal to half, and probability of minus a also will be equal to minus half. So into a plus half into minus a, that means this is equal to 0. So the expected value of t is equal to 0. So we will get expected value of Tk also will be equal to 0, and expected value of Ti at any time you can observe it will be equal to 0. So Rx of Tk and Ti will be equal to expected value of x of Tk into expected value of x of Ti. This is equal to 0 into 0, which is equal to 0 if the difference Tk minus Ti, if you take the difference, if it is greater than t, that means you are observing different parts of the pulses, that is, one is plus a and another is minus a, for like this. Okay, so if you are observing at time t, so you are observing at two different time instances, Tk and Ti, and if the difference between these are greater than t, that means both are in different pulses, both are different pulses. Okay, if this condition is satisfied, the autocorrelation function is equal to 0. So we got the a good result. That means expected value of Tk comma Ti is equal to 0 if Tk minus Ti is greater than capital T. Okay, this is one part. But what will be the situation if the expected value, if we are observing at the same time instant? Okay, if we are observing the time instant which is less than t, then now we will see now what will be Rx of Tk and Ti if Tk minus Ti is less than t. So it has been given the magnitude of Tk minus Ti is less than t. Now we will see what is the pulse. Okay, I will draw one pulse anyway. This is one pulse. Let's say this is minus a, and this duration is Td. Okay, and also it is given that the Td is having a minimum value of Td will be equal to 0, and the maximum value it can go up to capital T. And I told you, and also this is Td, and the pulse duration is T, and this duration will be nothing but T minus Td. Okay, that is very, very important notion. Now we will see how we can calculate the autocorrelation function, and this is plus a, this can be plus a or minus a, anyway it will depend upon the duration anyway. Okay, for the convenience now I am showing like this. And what is the distribution for Td? The capital F of Td is nothing but, you see here, this is a uniformly distributed. It has been given that it is uniformly distributed in the question. Okay, it is uniformly distributed. Okay, so what will be? It is uniformly distributed in the interval 0 and t. So the distribution will be 1 by t, because this is a uniform distribution between 0 and t. So this amplitude will be 1 by t, because total area, the area will be equal to 1, right? That's why. Now we will see how to calculate this. Okay, it has been given that the distribution is it is a TD is a small number and it is uniformly distributed between 0 and t. Now we want to find the Rx of Tk and Ti, which is nothing but expected value of x of Tk, okay, x of Tk into x of Ti, okay, x of Ti. Now we will, and we assume that we are considering the interval, that means Tk minus Ti is less than t, capital T. Okay, now we will consider a point here. How we can calculate this? Okay, I will consider the point Tk. I will consider the point Tk equal to 0. Okay, if Tk equal to 0, and this is just an assumption. Okay, assumption. If Tk equal to 0 and Ti is less than Tk, then you can consider Ti anywhere here, right? Ti can be anywhere here, and you know that this duration we have already calculated, T minus Td. Okay, then what is our condition? Our Ti minus Tk minus Tk, the magnitude of this, that means if I am taking Tk as at the origin and then Ti is somewhere here, then this difference Ti minus Tk, this difference is nothing but Ti minus Tk, the magnitude. This number should be less than some value which is delta here, should be less than this interval. If it goes beyond this interval, then Ti would be somewhere here in the second pulse. Okay, the pulse which is just before the 0th pulse, or we can say it will be here somewhere. So we should have a condition that Ti minus Tk should be less than this duration. That means, say this is delta, should be less than delta. That means, what is your delta here? You know this. What is your delta? We have already calculated the delta, given that. Okay, anyway, I will use next page. So Ti minus Tk should be less than some delta. And what is delta? Delta has been given here. You know that this is Td. So delta means actually the total duration is T. So delta is nothing but T minus Td, as I shown here, same. Okay, so this should be less than, this is, sorry, T minus capital T minus T. Okay, so Ti minus Tk should be less than delta is T minus Td. Okay, understood? Or I can write it in another way. Td should be less than T minus Tk minus Ti, Ti minus Tk. Okay, Tk, the magnitude. Okay, so it can be written like this, Tk minus Ti. Okay, I have written like this, Tk minus Ti. Am I correct? Okay, Tk, this is Tk, higher value is Tk and lower value is Ti. So I can write like this, Tk minus Ti, that is better. Okay, Tk minus Ti. Okay, Tk minus Ti. So here also I can write Tk minus Ti. Okay, Tk minus Ti here also. Okay, now this can be written as Tk minus Ti. Okay, and we are considering actually Ti as small value and Tk as higher value. Tk is 0 and Ti is below 0. That's why in this case. Now we have, if Tk minus Ti magnitude is less than T, then we can write Rx of tk ti as expected value of x of tk into x of ti. Okay, this is our simple expression. But if we know td, then it is nothing but the conditional expectation over td. That means x of tk, and this td is having a constraint that td is less than t minus tk minus ti, if td is given. Okay, so this is the condition. So the maximum value for td will be, t minus tk minus ti. This is the maximum value. If td is having a limit, that is, we are expressing this condition, expressing this condition in terms of td. If td, because we know that td is a random variable with some density function, and we know what is the density function, so we are making use of that idea. Okay, so if td is having a maximum value of td is t minus, capital T minus the absolute value of tk minus ti. If td cross this limit, then it will be nothing but the next pulse, it will not be in the same pulse. Okay, so Rx of tk ti is nothing but the expected value of x of tk into x of ti, given that you know the td. So you have to average it over all possible values of td, then you will be getting x of tk, expected value of x of ti. Okay, you have to average it over all possible values of td. So how will we calculate this? You know that this x of tk can take plus a or minus a, and if both are in the same pulse, if tk and ti times are in the same pulse, then you will get here plus a again for ti, and if this is minus a, again you will be getting minus a. So if you take the product, of these two, you will be getting a square. Again also here also, if you take the product minus a into minus a, again you will be getting a square. So whatever be the value, you will be getting the product as a square. So expected value of a square given td. And what is the condition for td? It has been given the maximum limit for td is nothing but t minus tk minus ti. Okay, but we put tk minus ti as some tau. Okay, so that is the time difference tau. Okay, this is the time difference. Okay, time difference. So this is nothing but Rx of tk and ti, but you will be putting it as some time difference. So this is nothing but a square is a constant into a square, we will say like this. Okay, integral, you have to expect, you have to find the expectation, a square into, you have to integrate over td. That means what is the distribution for td? Td having a distribution 1 by t. Okay, 1 by t, it is having a distribution 1 by t dtd, and td changes from 0 to the maximum value of td is nothing but t minus tk minus ti, the absolute value. So we can put this tk minus ti as tau, then Rx of tau will be equal to integral 0 to t minus magnitude of tau a square by t into dtd. Okay, dtd, and given that your tau and the magnitude of tau is less than capital T, then only you are considering the same pulse. Okay, otherwise you are considering two different parts of the pulse which are at different time instances, and they are not matching. That means if one is plus a, other will be minus a. If one is minus a, other will be plus a. Different parts of the pulse after time duration t. So you can integrate this dtd. So if you are integrating this, it will become Rx of tau will be equal to integral 0 to t minus tau into a square by t dt, which is equal to a square by t into td, and the td changes from 0 to t minus tau maximum. So this is equal to a square by t into, if this is equal to t minus tau, okay, a square by t into t minus magnitude of tau. So this is equal to a square by t into t minus a square by t into tau. So this is equal to a square into 1 minus tau by t. You can see here this is the autocorrelation function. So this is how we can find the autocorrelation for this sequence. So Rx of tau is equal to a square into 1 minus tau by t, okay. So this is equal to, we can solve it, we can represent it, okay, like this. You can see this is the equation of a triangle anyway. This is like this, and a t, this is a t, and after t this is tau, okay, and this is minus tau. So this is tau equal to t, and for tau greater than t, this value, the function is having a value 0, and for tau less than minus t, again the value is 0, okay, and the maximum value you will get it as a square. You can check this graph, okay. This is the equation of a straight line to the positive and negative side, because there is a absolute value. Now you can see many properties here. You can see Rx of 0 is equal to a square, and also if you take a point tau 1, let's say, then this is minus tau 1, and both these values are same, then Rx of tau 1 will be equal to Rx of minus tau 1, okay. Many things you can see, and Rx of tau will be equal to 0 for tau greater than or equal to t. That means if tau is greater than t, then what is the meaning? This is tau, this is the time, this is the point, you can say this is t, and the time difference, you can say this is tau. If this tau is greater than t, means you are considering a different pulse. That means you are considering a point in this pulse and you are considering another point in this pulse, and you can see that these are independent and they are uncorrelated. Since they are uncorrelated, because the value here it is minus a and this is plus a, and there is no relation between these two values because they are generated randomly as a binary sequence. You know, that is a Bernoulli trial, something like that. So the autocorrelation function Rx of t, there is no correlation between these two, it will be equal to 0. That's why we are getting here it as 0, okay. So here actually no correlation, and here also no correlation. So two pulses, suppose you are considering two pulses. For example, if you have a pulse here like this and this pulse same like this, then both are correlated highly. So in this case actually you will be getting a maximum number. So this kind of this kind of idea is used in synchronization in communication systems. That means you may transmit some signal and the receiver will be receiving it. Now you have to find what is the starting point of the pulse. So the transmitter will be sending some pilot signal, and the receiver will be having that same pilot signal which is locally generated at the receiver, and your pulse will be correlating with the received signal, and wherever at some point you will be getting a maximum matching. That means the delay tau equal to 0. So if you are getting a maximum matching at some point, that means that is the starting point. There is no other way to find it. There are a lot of other techniques anyway. So this is one of the very famous techniques. This is how you can synchronize the transmission signal and the received signal in the communication system. So I would like to add one more point here. You know now the Rx of t is nothing but a square into 1 minus t. So you have you obtained Rx of tau, okay, obtained Rx of tau. Now you can find the power spectral density of this signal. That means spectral density of your pulse anyway, okay, of this pulse. How to find it, the power spectral density? If you take the Fourier transform of Rx of tau, then you will be getting Xx of f, and this is nothing but the power spectral density we have already seen in the last lecture, PSD. And this relationship, that means the Rx of tau is having a Fourier transform, Rx of tau is having a Fourier transform Rx of tau is having a Fourier transform Xx of f, and Xx of f is having an inverse Fourier transform as Rx of tau, okay. So this relationship is known as the Wiener, I will tell you, okay, this is known as this relationship we will call it as Wiener-Khinchin. This is the name of the scientist anyway, researchers, Wiener-Khinchin relation, okay. This I forgot to explain in the last lecture, okay. So this is nothing but the Wiener-Khinchin relationship, and it's very important. You should know this is the relationship, okay. I hope everything is clear to you. Inshallah, we will discuss the next part, as the next topic will be the Markovian process, okay. So in the next lecture we will discuss Markov process.